Hello, and welcome to the lecture, Warming the Earth's Atmosphere, Energy Transfers, and Temperature Variations. Whenever you start talking about weather, of course, you have to start with the sun because the sun is what provides the atmosphere energy to drive all the processes that take place within it. So understanding how the Earth actually heats up and how this energy is transferred to the atmosphere to, result in these processes is essential. So again, to start out, the sun is where everything begins with the development of weather and the heating of the Earth's surface. So whenever you start talking about the sun, you have to look at what forms of actual energy it puts out. Well, whenever you start talking about the sun, one of the most common misconceptions is students think it only puts out a certain wavelength of energy. In all actuality, the sun is putting out all of these different wavelengths of the electromagnetic spectrum. Now, what reaches the surface is completely different than this because, as you can see here, the atmosphere is a selective either absorber or transmitter of certain wavelengths of this actual electromagnetic energy coming from the sun. Now, one of the misconceptions here is you notice that the UV radiation does not reach all the way to the surface. Well, this diagram is somewhat correct. You can see there to the far right of the purple where it's actually down a little bit. That's basically the good, not so actual damaging UV radiation that actually reaches the surface there. This up here is actually the bad UV radiation that our atmosphere selectively absorbs so that it doesn't reach the surface. So understanding what wavelengths of energy actually reach the Earth's surface is going to explain how the atmosphere is actually heated up. Now, with this, what you're talking about is the global energy budget. Okay, so whenever we start talking about this global energy budget, what's really unique about this is only 51% of the total radiation, so out of the 100% radiation coming to our planet, only 51% of it reaches the actual Earth's surface. And then once it reaches the surface, it actually goes through this transfer and this change of the type of energy from the UV reaching the surface to infrared that is actually released from the surface. And so you'll get a better understanding of what's going on with the atmosphere as we progress through not only this lecture, but also throughout the course, because it's going to all start to make a lot of sense of how the atmosphere actually works. So again, whenever we start out, we're talking about the atmosphere being in a complete balance where you have that 51% and you have certain amounts leaving and certain amount being retained within the Earth. Okay, so one of the first concepts of actually heating the Earth you have to understand is what is called the greenhouse effect. The greenhouse effect is basically where the Earth kind of, in a sense, traps outgoing heat. But if you want to more accurately, explain what's going on, it's that it is actually absorbing outgoing heat and re-radiating it back towards the surface. So one of the big things that you actually want to recognize with this is that incoming solar radiation is going to be in the UV wavelength. Okay, and that UV wavelength is actually going to be transformed once it reaches the Earth's surface. It's going to heat up the Earth's surface, and then the surface is going to release infrared or heat energy. Well, these greenhouse gases, what they do is they absorb that outgoing infrared radiation, but only some of it. Okay, so think of it like a Afghan blanket where you have holes in this thing, right? And so it allows some to actually escape, but then it traps some of it. And then whenever it basically traps, or more accurately, absorbs that outgoing radiation, it re-radiates it back towards the surface, keeping our planet warm, specifically at night. Because once our planet rotated into the nighttime part of our rotation, we would lose all of that radiation and our oceans would instantly freeze. So you would see a drastic drop in temperature if we did not have these greenhouse gases. But because we do, our nighttime temperatures are able to be moderated because of that. And so that's what you're actually looking at there. So this right here is all part of our global energy budget and how the Earth actually keeps some of its warmth. And by keeping some of its warmth, the greenhouse gases play a very, very important role. Now, what else can actually happen to the light whenever it comes in? That light can be either absorbed, reflected, or scattered based on what it's actually interacting with. Well, whenever you start talking about blue skies, one of the most common misconceptions is what causes blue skies, and most people will say reflections off the oceans. That is so inaccurate, actually, because then, okay, that just doesn't make sense, especially at night when there is no light. Okay, so what's really happening there with that light as it's coming in? It is actually being scattered. Okay, it's a process known as Rayleigh scattering, and it's being scattered into that wavelength of the visible spectrum where you start to see, the blues. Okay, so that energy is coming in at a very high energy level, and then once it hits the molecules of our atmosphere, it gets scattered out. Okay, and then as a result, that gives us the blue sky appearance. Well, the red sunlight appearance, like of sunsets, what's different there is that the wavelength is actually it's having to pass through much more atmosphere, so there's much more scattering that's taking place, and it pushes that all the way to the red end of the spectrum. Okay, and so we'll be talking more about air particles and stuff like that, and it'll make a lot more sense as we progress throughout the course. All right, another characteristic or another term that you're going to have to become familiar with is albedo. Albedo is basically a meteorological term for reflectivity. So whenever you start talking about something with a high albedo, that means that it's going to reflect a lot of the sunlight, which means it is not being absorbed. Now that's a big deal right there, because another misconception that students have is that, okay, it doesn't really matter if it's reflected or absorbed. Well, that is actually untrue, because if the example I always like to use is which car is hotter in the summer, a black car or a white car? And of course every student says, well, it's a black car. And the reason that the black car is actually hotter is because those darker colors have a lower albedo, and so they actually absorb more of that incoming radiation. Well, of course, because of Kirchhoff's law, which is basically good absorbers are good emitters, then the more energy that this object actually absorbs, the more infrared energy or heat it's going to release. If it reflects, it's just reflecting UV radiation. So yeah, you'll feel a little bit of warmth from that, but really what you're going to do is get a really nice suntan. And so that's why in the winter, if you're a skier, you'll notice that some skiers actually get sunburn on their faces. And it's because the sunlight is reflecting off of the snow up onto their face and giving them that sunburn. That heat is not what gives you a sunburn. Okay, and so this is the whole concept there of understanding how that energy actually works in the actual atmosphere itself. Okay, so to kind of wrap all this up and everything, what you can actually see here is you have the incoming energy. Some of it is absorbed by the atmosphere, some of it is absorbed by the surface. Some of that energy could be reflected by clouds. Some of it is actually reflected by ice particles that are way high in the atmosphere and stuff like that. So what you're looking at is the interactions here of the actual atmosphere itself and what it does to that incoming solar radiation. And that's key, because what that does is the sun's energy is actually what drives all of these weather patterns and weather systems, as well as heating the Earth's surface processes that we're going to be looking at much more in depth. Okay, in this part of the lecture, I want to discuss methods of energy transfer. So in other words, now that energy actually gets into the actual planet itself and heats the Earth's surface, how is that energy going to be transferred within the atmosphere itself, as well as from the Earth to the atmosphere? Okay, so whenever you start talking about the three primary methods of energy transfer, there's really three ways that you actually have it. It's radiation, conduction, and convection. Okay, whenever you start talking about these primary forms here, radiation is a form of energy transfer where the energy is being transferred from the sun to the planet itself, which we've already talked about in the last part of the lecture. Well, as that radiation comes in, it's going to heat up the actual Earth's surface. And so whenever it heats up the Earth's surface, then what's going to happen there is the air is in contact with the ground. And then so whenever that air becomes in contact with the ground, energy is transferred from the ground to the air. That is called conduction. So anytime you have the transfer of energy by objects touching, that is called conduction. And so then what actually happens is after that energy is actually transferred to the air, you change the density of that object, you make it less dense, and so that parcel or bubble of air is going to rise up. And because it's warmer than the surrounding air, it's going to transfer its energy to the air particles surrounding it. It's kind of like the boiling water effect. Okay, you put a pot of boiling water on the actual stove. The radiation is actually from the stove is heating the bottom of the pot. Then the pot is in contact with the water on the bottom of the pan, and it's actually transferring the heat from the bottom of the pan to the bottom of the water that's in the pan, and then you'll notice that it starts to bubble. Well, those bubbles are really just water vapor, so you've actually changed the phase of it. But as those bubbles come up through the water and leave the boiling water as steam, it is actually transferring energy to the rest of the water that's not along the bottom. And so that's called convection. And so whenever you start looking at these actual processes where you have all of this circulation of air going on right here, solar radiation comes in, heats up the surface is in contact with the actual air right there. That air will start to rise, and as it rises, it's starting to actually exchange energy. Okay, so all three of these are processes that exchange energy. And then, of course, now we do have another form of energy that a lot of people are not aware of, and that is what is called latent heat. Latent heat is energy that is stored in the phase of the actual object. So in this case, it's water vapor. So whenever you have water vapor that is at the surface, and you can't see it right here, as it starts to rise, it's losing energy. And as it loses energy, you guys will learn that right there is where it actually reaches what is called its dew point. And so right at that point, it went from water vapor that we can't see to liquid water. That's the base of the cloud. Well, as soon as it changes a phase, what that does is that means that little water droplet, one of the tiny little water droplets there, is actually releasing energy to the surrounding area. Okay? And so to the surrounding air. And what that does is that heats up that air, making it want to rise as well. And so this is the whole concept behind why you see clouds have these fluffy tops like that. Because all that is you have latent heat exchanges going on inside of that cloud where the cloud will continue to rise. And latent heat exchanges, depending upon how much water vapor there is, have a lot of energy in them. Okay? Now, you'll understand this whenever we get into the next module of how clouds actually form. And then another method of energy transfer that is not depicted in any of the diagrams is advection. Not convection, but advection. That's the horizontal motion of energy transfers. Okay? Now, one thing that, is kind of common, but I'll just go ahead and put it out there to make sure everyone understands, is everyone knows that energy is always going to transfer from hot to cold objects. Okay, so energy, you're always going to go from higher energy levels to lower energy levels. That's just how energy transfers. And so what we're going to be looking at here coming up very soon is how objects heat differently, specifically objects on the Earth's surface. Now, to conclude this, how does this all relate? Well, what this basically shows, or if you remember in the troposphere, which is where all of our weather takes place, you can actually see that the temperature decreases with height. Okay? This is 100% proof that our atmosphere does not heat from the top down. Because if it did, where the sunlight first comes in, it would be hotter up here and colder down here. You would just basically see a nice little curve going this way. But because you see this variation right here where the temperature gets colder, this is an indication that our atmosphere actually heats from the ground upwards, because it's hotter down here when it's closer to the ground, and it's colder up here where it's farther away. Okay, which is a really big concept to actually understand, because that'll explain to you a lot of other processes. Now, up here in the stratosphere, of course, right through there, what explains this temperature increase? That is the absorption of incoming UV radiation by the ozone layer. So this is where your ozone layer is at. And that's why you see that temperature increase. It's because ozone actually absorbs incoming UV radiation. And then, of course, once it absorbs it, good emitters or good absorbers or good emitters, it re-releases as heat. And that's why you get this portion of the atmosphere being warmer. Up here it's colder, because of course, there's no ozone layer. There's nothing that's going to absorb that energy. But then up here, you can see that, man, it really jumps up significantly. And that is really just because there are fewer particles of air. And of course, hopefully everyone knows that whenever you measure the temperature of something, all you're really doing is measuring the molecular motion of an object, of atoms, right? Or in this case, air, excuse me. And so whenever you start talking about, well, there's very few air molecules and they get a little bit of sunlight, they get that sunlight coming in, well, they start moving like crazy. That's going to give you a thermometer reading that is very, very high. Okay? But please don't let that be misleading. If you go to the edge of the atmosphere, it is going to be exceptionally, exceptionally cold. Again, this is like a false reading of the actual temperature. Okay? It's just because there's so few air molecules up there. Okay. So now to move on to the last part of our little lecture here, which is going to be what we're called the controls of temperature. Now, these are factors that are going to influence the temperature of our planet. This is very important not only for climate, but you can also take many of these actual concepts and apply them to local temperatures. Okay, so it's a way that you can kind of explain what explains the temperature variations across the globe. Well, whenever you start talking about the number one control of temperature, that is going to be latitude. Why? Because latitude actually influences how direct the sun's rays are on the planet. Because we are a round planet, and the sun's rays are coming in, it's going to always hit different locations with different amounts of directness. All right, so as you can see here at the North Pole, the sun is not hitting the pole very directly whatsoever. Even in the summer, it's not hitting the poles very directly, so the sun doesn't get very, very high in the sky, right? So what that does is that influences your local temperatures, because now you're looking at something like this. Because those rays aren't very direct, that location is not going to get very hot. But as you go farther towards the equator, you're going to notice that the sun is going to appear higher in the sky. What that's going to result in is the rays being much more direct, as you can see on the image on the left, which in return is going to actually heat up that region more, causing higher temperatures. And so this is why the equator at certain times of year, in 23.5 degrees north, or the Tropic of Cancer, or the Tropic of Capricorn at 23.5 degrees south, are basically going to be the hottest places on the planet at certain times of the year. Okay, it's all about this angle of sunlight that really actually, plays a primary difference in why Minnesota has winters unlike Florida. Okay, so one of the most common misconceptions is that the seasons are a result of variations in distance from the sun. Well, as you can see here, we are actually farther away from the farther away from the sun during our summer in the northern hemisphere than we are in the winter. So it really has to do all with that tilt and the actual directness of sunlight. And so because of this actual this tilt that the planet has, and you notice that the tilt and as the Earth orbits around the sun, the tilt never really changes its direction. It's always pointing towards the North Star. Okay, so as it revolves around the actual sun, which hemisphere is actually tilted towards the sun determines the seasons. And so in the case of July, you can see that the northern hemisphere is tilted more towards the sun. That means that the rays are going to be more direct on the actual planet on the northern hemisphere, which results in its summer. Well, if you go to the southern hemisphere, our summer here in the northern hemisphere is the southern hemisphere's winter. But then whenever you go over here to January, you notice that the southern hemisphere is tilted towards the sun, and so that's their summer, and we're tilted away from the sun, which is our winter. So it really has to do about the orbit of the Earth and our tilt that actually is what causes the seasons, and that, of course, is all related to differential heating. And so the one thing that I like to do in this class, and I like to do really kind of in all my classes, is I like to show some of the math of how this is actually works, and something that it possibly relates to. And so whenever you start looking at this angle of the noon sun, where it's actually located, this is a tool that you can use as a meteorologist to determine what the angle of the noon sun is, because this is called the analemma. So what this shows is it shows where the sun is located directly overhead or at 9 degrees at any given date throughout the year. So if you're talking December 22nd is about right in here, and what you will notice is on the left-hand side of the graph, you have 0 degrees, which is the equator, 23.5 north, 23.5 south. So on December 22nd, if you went out and you were, let's say, in Australia, on December 22nd at noon, you would actually look straight above your head. And that's where you would actually see the noon sun. The noon sun would be directly overhead. In the northern hemisphere on June 22nd, the first day of summer, you would actually be at 23.5 degrees, which would be, that would probably be maybe... I'm just kind of guesstimating here. I'm going to say about North Carolina, maybe a little bit lower between North and South Carolina. That's where the noon sun would be directly overhead. Oh, no, I'm sorry. It'd be even farther south. I'm sorry. It would be, because Orlando, Florida is 28 degrees. So 23.5 degrees would be like Central America. And Central America is where the noon sun would be directly overhead. Okay, so that's what this does. So let me give you one more example here. Let's just say April 17th. Where is the noon sun on April 17th? So there's the 10th. So the 17th is about right here. That would be at about 9 degrees north. So if you were located at 9 degrees north on April 17th, you would notice that the noon sun would be 90 degrees or directly overhead at that location. Okay, now how does this apply? And the reason that I like to teach this is because this is what Tom Hanks used in the movie Castaway. Inside one of his caves, he actually drew the analemma, and he used this to actually get off the island, because, of course, that differential heating has an influence on other things like pressures and wind and how things actually move on this planet. How the atmosphere moves on this planet, which makes it super, super interesting. Okay, so now we're going to get into what actually controls these variations in temperature. Okay, latitude, like we just went extensively into, is the number one control. Another control of temperature, another thing that actually influences temperatures of regions, is the differential heating of land and water. So whenever you start talking about differential heating of land and water, the first thing that you want to understand is specific heat. specific heat is really how much energy does a substance have to take in to actually change 1 degree of Celsius, okay, in temperature. So whenever you start talking about something with a high specific heat, then what that means is it needs to take in more energy to raise 1 degree in temperature, okay? Whereas something with a low specific heat has to take in less energy and therefore is going to raise 1 degree of temperature a lot easier. And so whenever you start looking at this and you start comparing continental locations, okay, to coastal locations, you have to look at the differential heating of land and water. Whenever you look at this, you're going to start to notice that water has a higher specific heat, so it takes more energy. So it's going to actually stay cooler than somewhere that would be located like in the center of a continent. Okay? So what that does is that water keeps coastal areas a lot cooler in the summers than it does in, than inland, than like, the middle of Missouri or something like that, where you're right in the midland areas of our continent. And so this is one of those things that you really kind of want to understand, because this can explain why coastal regions tend to have more moderate temperatures because of the differential heating of land and water. And so that's one of the big things that you want to look at. Okay. Now, the other thing that you have to kind of note here is that water will retain that energy longer than land will. So remember, they're going to heat up during the day, but then at night, when they're no longer receiving energy, they're going to release that energy to the atmosphere. And so whenever they release that energy to the atmosphere, the land is actually going to release its energy a lot faster. So you're going to see more inland areas getting cooler a lot faster than you will coastal areas because of that differential heating of land and water and that release of latent heat. Or excuse me, the ability of the object to release the heat. And this is a perfect example right there. Look at the temperature variations for Dallas throughout the year and look at those for San Diego. Because San Diego is actually more coastal, you're going to notice that you have a temperature fluctuation throughout the course of a year that is not very big. And that's because of the moderating effects of the ocean. Whereas if you get somewhere in the Midlands, like in Dallas, Texas, you notice that it's not near a body of water. And as a result, you're going to have these drastic temperature changes throughout the course of the year. Now, of course, you can relate this same type of graph. It'll look same exact even if you put it on a daily basis from like a 24-hour period. You're going to get the same type of graph. The only thing difference is they're going to be inverted because now you're going to gain temperature and lose temperature at a location. But it's really all about how that water or lack of water actually influences the temperature. Next thing that I want to address is ocean currents. Whenever you start talking about ocean currents, they have a huge effect on temperature. Now, what a lot of people do not realize, most people look at this and they're like, oh, you must be in a tropical area. That is actually incorrect. That is Scotland. Okay? So whenever you start looking at places in Scotland, you're like, how are there palm trees in Scotland? Well, the primary reason is because Scotland is actually influenced by the warm Gulf Stream current. So currents play a huge role in the climate and the temperatures of a locale. And so whenever you start talking about California, why is California just like so moderate like throughout the course of the year? Okay, if you start looking at coastal California, everybody loves coastal California. It's not too hot, it's not too cold, right? Well, that's the water and heating effect. But at the same time, look what current is out there. That's a cold California current. Okay, and so what that do is that cold current is actually going to take places that would normally, like at low latitude, so they're down here getting a lot of sunlight, so they should be really hot. That cold current is actually going to help reduce those temperatures. So instead of being, an average temperature of 90 to 95 in the summer, their average temperatures are like 80, 85, and it's all because of the influence of that cold current. So as you look through a bunch of these different locations, what you're going to notice is you're going to notice that each location has a different type of current, and if it's a warm current or a cold current, is actually going to have an influence on the actual temperature. Another variable is going to be basically be, elevation. Are you up in the mountains, or are you in, a basin or something like that? This is kind of self-explanatory. The one that, a lot of people don't know is over here you start out warm, right? And you go up the mountains. So just imagine this air moving. Well, you're going to get up here, the temperatures would be cold. So if you live in Colorado or something, you are up in the mountains. So you're going to have a lot colder and cooler summers than you would normally, just because of elevation. But the one that people don't know about is this over here. Whenever you start coming down, you have these winds come off the mountain. That air is actually compressed, and so what it's going to do is it's going to actually heat up that air. So you're going to experience warmer temperatures over here than you normally would if there weren't any mountains in this area. Now, that influence doesn't only have an effect on the temperature, but it also has an effect on the precipitation levels. And so these areas over here do not get a lot of rain, and that's why they are referred to as rain shadows. And if you've ever seen the movie Holes, that is a perfect example of a rain shadow. If you've seen the movie, you know how the lakes actually dried up, and that's because as this air came down off the mountain, it warmed up and it evaporated those lakes. And then, again, referring back to it, you notice that it was a small mountain. Where were the onions? They were up here. Why? Because it was always raining. Okay? It wasn't as big a mountain as this, so they just had rain up there. But it's kind of the concept of holes. So, if you're in the rain shadow or not in the rain shadow will actually have an impact on your local temperatures as well. Which way is the slope facing? Okay, so, if you live in mountainous areas, you're going to basically say, if my house is on a south-facing slope, you're going to notice that it's going to be a lot more direct sunlight than someone on the north slope. And you can see here, notice the change in vegetation. This is a south-facing slope, so that means the sun is always over here, and it's hitting directly on that side. Well, notice you have just grasslands, but over here, the sun's not as direct, so you're not drying out the soil, so now you get some different vegetation growing. Well, if you take this and magnify it to large scale, you will also see that, is your town if you have mountains that are running east-west, and you have a town that's on the south side of the mountains and a town that's on the north side of the mountains, you're going to notice a significant temperature difference because of that. Urbanization has effect. This right here is referred to as an urban heat island. So you can see simply by, what's the ground surface like, because cement is going to absorb more UV energy coming in. So it's going to, of course, make it hotter. So you don't get hardly any reflectivity whatsoever off of your concrete and off your buildings. This is one of the primary reasons that a lot of people have actually gone to putting in rooftop gardens, because what will happen there is instead of the energy being absorbed by the concrete, which then of course makes you turn up your air more, what's going to end up happening is your soils, that your plants on your rooftop garden are going to absorb that energy, and you're going to notice that if you're in an apartment that's beneath it, it's going to be a lot cooler. But you're still absorbing that energy, but it's being used for other processes. So that's kind of a big science concept right there. It's tough to understand, but if you get into other classes and stuff, you'll start to see how it actually works. And then last but not least is albedo. Okay, whenever you start, actually, I'm sorry, it's not last. Albedo and cloud cover are the last two concepts. So whenever you start talking about surfaces, right, this is big, especially in wintertime precipitation or wintertime temperature forecasts, because if you have ground that is actually snow covered, what you're going to notice is the nights are going to be a lot colder than you would in the winter if the ground was not snow covered. And so meteorologists have to take this into account whenever they're making their wintertime forecasts of temperatures. Because remember, if there's a lot of reflectivity, there's not a lot of absorption going on, so there's not going to be a lot of energy that is going to be really released. And so any amount, so you see you only get 10 to 15% absorbed, that means you're only going to have about 10 to 15%, which means your nighttime temperatures are going to be real cold the later you get. As compared to here, it's going to be significantly different because you're talking about 70% absorbed, so that means you get to release 70% of the energy over the course of the night, and that means that the temperatures are not going to be really kind of cooler in the cold in the winter until the early hours of the morning. So it's all about these energy exchanges and how they actually work. And then the same thing applies to cloud cover. It depends on what time of day you're actually looking at. Okay, if you're talking about cloud cover during the day, well, that's going to block from some of the radiation from reaching the Earth's surface, so you're going to have cooler temperatures. Whereas if you have clouds at night, you're going to notice that the outgoing infrared energies, some of it is going to be absorbed by the cloud and re-radiated back towards the surface. So if you had cloud cover at nights, meteorologists are going to forecast warmer temperatures at night than they would on a night where there's absolutely no clouds whatsoever. So over here, you're going to see a large temperature variation from daytime to nighttime. Okay, so you're going to see a significant drop in temperature, whereas over here, you're going to see more of a moderate drop, and that's all because of the cloud cover. Okay? And so whenever you start to look at this, these are the variables that atmospheric scientists use to actually forecast local temperatures. They, the effect of latitude and proximity to oceans and all that stuff is already kind of taken into account. But whenever you start talking about local temperatures, you do have to look at, okay, what's the land like? What time of year is it? But really, this one is the one that plays a big role, which is the cloud cover. What's the cloud cover during the day? So hopefully this video does a lot to help you understand the concepts. And if you have any further questions, please don't hesitate to contact me.